You've probably heard of enzymes as biological catalysts. To understand the role of enzymes in speeding up chemical reactions, first, you need to have some knowledge of the kinetics of chemical reactions. The figure here shows the energy profile for two types of reaction. Endergonic means energy absorbing. The reactants have less energy than the products, and the reaction will not proceed without a net energy input. All the anabolic reactions in our body fall into this category. On the contrary, if the reactants have more energy than the products, a net amount of energy would be released. This type of reaction is known as an exergonic reaction or energy-releasing reaction. Catabolic reactions belong to this category. It is worth noting that in a reaction, there is an energy barrier between reactants and products. Reactants have to absorb enough energy to break the chemical bonds in the reactants, so that new bonds in those of the products can be formed. Therefore, in all reactions, even in an energy-releasing reaction, a certain amount of initial energy input is required for the reaction to proceed. Take the hydrolysis of sucrose as an example. Sucrose is a disaccharide combination of a glucose molecule and a fructose molecule. During the process of hydrolysis, energy is needed to break the original bonds. After new bonds are formed, a larger amount of energy is released, and therefore hydrolysis is an energy-releasing reaction as a whole. The initial energy input required to overcome the energy barrier is called the activation energy. The situation is like pushing a rock over the hump, which represents the energy barrier, at the top of a hill. This action requires sufficient energy. Once the rock is over the hump, it rolls to the bottom of the hill. The activation energy of a chemical reaction is closely related to its rate. The higher the activation energy, the slower the chemical reaction will be. So, what has the activation energy got to do with enzymes? Enzymes are biological catalysts in our body. They speed up chemical reactions by providing an alternative pathway with a lower activation energy barrier. Let's take a look at how enzymes catalyzes the hydrolysis of sucrose. A large amount of energy is needed to break the strong glycosidic bond between the glucose molecule and the fructose molecule, if no enzyme is used. By binding with the substrate, the enzyme helps stabilize the intermediate form of substrate and therefore lowers the energy barrier of the reaction. To make it easier to understand how enzymes provide an alternative pathway with a lower energy barrier, let's return to the scenario of pushing a rock over the hump. Pushing a rock over the hump at the top of a hill is energy demanding. If a tunnel is drilled through the hill, an easier route is available. Pushing the rock through the tunnel is an alternative route which requires less energy. In the same way, a reaction can proceed faster with enzymes as catalysts. Now look at the energy profile again. This time, the figure shows the energy profile for an enzyme-catalyzed reaction and an uncatalyzed reaction. We can see that enzymes can provide a different reaction pathway with lower activation energy, no matter whether it is an endergonic or exergonic reaction. This explains why enzymes can speed up both anabolic and catabolic reactions.